Welcome back, everyone. I put this video together for my calculus class. This is a quick video talking about how to analytically or algebraically find the concavity for a function. And so a couple things to talk here first. Concave up is this shape right here, and concave down is this shape right here. And we get all of these things from the second derivative. And I'm going to show you two examples on how we are going to go about that. So let's get started. We have our first example here we use blue here, for f of x is equal to x to the fourth minus 4x cubed. We are going to find the first and second derivative. So it starts off here with the power rule. First derivative would be 4x cubed minus 12x squared. Now, if we remember from previous lesson and versions from the first derivative, we'll get increasing and decreasing intervals. We'll get critical values by setting the derivative equal to 0, and we get that stuff. And then we can also get extrema, maxes and mins from the first derivative. But now we're going to kind of apply the same thing with the second derivative. So the second derivative is going to be 12x squared minus 24x. And so it starts by taking the second derivative and setting it equal to 0. So we're going to factor out a 12x, and we'll get x minus 2. So in the first derivative, we call them critical values. In the second derivative, we call them possible POIs. And we see here that at x equals 0 and 2, that we'll have possible POIs. Now, a POI is called a point of inflection. And what that tells us is where a graph changes from concave down to concave up, or vice versa. Right here, we would have a POI because it changed from being concave down to concave up. So very similar process here from the first derivative test stuff. We are going to make a number line from 0 and 2. And we will have these intervals now from negative infinity to 0, between 0 and 2, and from 2 to infinity. And what we're going to do is we're going to pick test values for the second derivative. So I'm going to evaluate f double prime of -1, f double prime of 1, f double prime, I'll pick something greater than, I'll put 5. Now, if we get a positive answer, we are concave up. If we get a negative answer, we are concave down. Okay, so I go to the factored form, which is a lot easier to go to. I'm going to plug in -1. If I plug in -1 here, that gives me -12. If I plug in -1 here, that gives me -3. I get a negative times a negative, which makes this a positive, which tells me that this first interval is concave up. Then I plug in 1. I'll be positive and I'll be negative. Positive times a negative, that's a negative, which tells me I'll be concave down. And then I plug in 5, and I'll see that I got a positive times a positive, which is a positive, and I'll be back to concave up. So these wind up being my intervals of concavity, okay? And at those possible POIs, if I have a change in concavity, that makes it an actual POI. So right here at 0, I did have a changeover. So I do have a POI at 0, comma, and then remember, anytime I need a y value, I go back to the original function. So if I plug in 0 here, I'll get 0. At 2, I had a change in concavity as well. And if I go back to the original function and I plug in 2, that'll wind up being -7 16. So those are my point of inflections and my concavity intervals for this function right here. Now, it will always help to graph the original function, and you'll see how we are concave up to concave down and concave up. Okay, so I want to do one more. All right, so we got f of x is x cubed minus 12x. So we are going to start off by finding the first and second derivative. So 3x squared minus 12. Second derivative here is going to be 6x. We will set that equal to 0. So we only have one possible POI at x equals 0. We'll make our number line for 0. And then we'll pick our test points. So we're going to go f double prime negative 2, f double prime 2. I could pick anything, okay? And again, my intervals that I already have now, that's why I draw the number line. I go from negative infinity to 0 and from 0 to infinity. So let's see what happens when I plug in negative 2 to my derivative. I'm going to get a negative answer. So that's negative. That makes this concave down. I plug in 2. That's going to be positive. That'll make it concave up. So these are my concavity intervals. And since I do have a switch from one to the other, that makes a point of inflection at 0, comma, and again, this one by plugging in 0 to the original will be 0. So there's two quick examples on how to algebraically or analytically find concavity intervals using the second derivative. Thanks for tuning in.